and action.
Action! Bum, bum, ba-da-ba-dum, bum, 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 ba-da-ba-dum, bum, bum.
Okay, so we can begin looking at the bicycle through a kinematics lens. So we can calculate the velocity. He travels 1 meter in this delta t, and this delta t would be figured out through 2.5 seconds minus 1.6 seconds, and if we calculate that, we get 1.11 meters per second, and we can find the acceleration, which is just a change in velocity over the change in time. So we have 1.11 meters per second, which we just found, over 0.45 seconds, and we get 2.46 meters per second squared. And we can also find rotational kinematics for one wheel, and we know that the radius of one wheel is 0.35 meters. So to find omega, which is the rotational velocity, we can use this equation: velocity equals omega times r. So omega would equal velocity over radius, and we just found the velocity, which is 1.11 meters per second, and we know the radius because we measured it, so it's 0.35 meters. And if we calculate it, we get 3.17 over seconds squared, or 3.17 radians per second. And to find the angular acceleration, we can use the equation delta omega over delta t, and we know that the change in omega is 3.17 over second, and we divide that by 2.05 seconds, and we get 1.54 over second squared. So now we can look at this problem through an energy lens, and we know that the mass of the rider and the bike together is 77 kilograms. We know that the radius of the wheel is 0.35 meters, and we know that the mass of the wheel is 2.7 kilograms. So first we can find the kinetic energy. So 1/2 times the mass of the bike times 1.11 meters per second quantity squared. So we would get kinetic energy to be 47.53 joules. So now for potential energy, we'll multiply the mass times the gravity times the height. So 77 kilograms times 10 meters per second squared. And to find the height, we do this triangle again. So we know our displacement is 1 meter. And we know that we have an angle of 7.7 degrees. So we can just find the height to be the sine of 7.7 times 1 meter. And we get 103.18 joules for the potential energy. Now the kinetic energy of rotation can be found by multiplying the moment of inertia times omega squared. So moment of inertia could be found by mass times radius squared. So we know that the mass of one wheel is 2.7 kilograms, and then we multiply that to 0.35 meters quantity squared, and we get our moment of inertia, and we multiply that to our omega, which we found earlier, squared, and we get 3.33 joules. So now if we add all of these together, we get this total energy, 154 joules, and to find our power, it's just the change of energy over the change in time, so 154 joules over 0.45 seconds, and we get 342 watts. Okay, so now we can compare the energy of walking to the energy of biking. So for walking, the total kinetic energy we found to be was 944 joules. The potential energy was 1,206 joules. The total energy was 2,150 joules, and the total power was calculated to be 3,394 watts. And we found all of these just by adding the individual increments up and getting these. And the total kinetic energy for biking is 2,086 joules. The total kinetic energy of rotation is 146 joules. The total potential energy is 1,547 joules. And the total energy is 3,780 joules. Now this isn't much of a difference from the total energy of walking. It's only about a third larger, but the total power is much larger than the total power of walking, and that's because all this energy is expended in this much smaller period of time. So we get total power of 7,307 watts compared to 3,000 watts. So biking requires a lot more power than walking does. So our conclusion is that walking is probably more efficient when it comes to moving up ramps.